Hi guys, my name is Manish Kumar and today we will create system design of proximity service. So let's start with our step 1, and step 1 is understand the system well by collecting the functional requirements. So functional requirements. So what proximity service does? Proximity service lists all the business in given radius and let long. So if user want to say like, okay, tell me all nearby gas stations within 3 mile of radius, so it basically takes the let long of the user and like give all or list all the gas stations within 3 mile radius. So that is the key requirement. Second is the business owners should be able to add, update and remove the business. So these are the key functional requirement and we will focus majorly on these. We will keep out of scope like paging and order by, top ranking, etc. So we will keep them out of scope. Our major focus will be to design a system which can list all the business in given radius of a let long, and business owners should be able to add or update and remove the business. So let's go to our step 2, and step 2 is non-functional requirements. So latency. System should be low latency. So there should be low latency in the system. If I'm driving and like I need a gas station nearby, I need a result quickly, rather just like, I get out of gas and then the system is like giving me the response. And should be highly available, scalable, so should be able to handle peak load. And peak load could be anything, like for example, if there is a particular event on a location and like Justin Bieber performance or something like very popular event happening where like hundred of thousand people are traveling within an hour looking for their locations, finding the things, so there is a peak load. So system should be scalable to handle the peak loads. And what else? The consistency, maybe eventual consistent. And why I am saying eventual consistency, so I think if there is a new business came up and business owner feed the information into system, it is okay if it takes up to a day to start showing the information of new businesses or new updates. So I'll say it is okay to show new businesses and updates delay up to a day. But once the information is there, it should be consistent. It should not be like I'm refreshing, I guess see a business, again I'm refreshing, or I'm looking through other device, it is not appearing there. So it should be consistent in that way. So that's why I'm calling it eventually consistent system we need here. So guys, I think we are good on the non-functional requirement. It's time to go to our step 3. And in step 3, let's talk about APIs. So APIs, what I see here is like get one location or list of business where like user will give the let long, radius and maybe business type. So like for example, I'm looking for gas station, I'm looking for Walmarts, and we are saying radius, so our requirement here is list all business in the given radius. Okay, that's already recorded. So this will be one API. Then another API will be get post put delete v1 business and business ID. So users should be able to create a new business, users should be able to update the information, users should be able to delete the information. And here it will have ID and title and description about business and location and contact info, etc. Ranking and like review and things we are not considering in the scope of this design, so I'm not mentioning them, but those will also be the information we need to store here. So I think from API point of view, guys, users should be able to get the business list of businesses within a given radius, and the business owners will be able to create, delete and update the business information. I think we are pretty good on API side now, guys. So let's move to our next step, and that is our capacity math. So what is capacity math? What we need to do in this? So some people call it back of envelope estimate. In one of my video, I already told you I call it capacity math. So it's up to you what you want to call it. So in the capacity math, let's make certain few important assumptions here. So let's say we have 500 million user base, and let's say 200 million are daily active users, and they are doing how many 10 search a day. 10 seems to be higher on side, but okay, 10 search per day. So if we see query per second QPS, basically QPS will be 200 million is 10 raised to power 6 users making 10 search per day, and if we divide by 24 into 60 and we always round this number to 10 raised to power 5. So this come out to be 200 into 10 into 10, which is 20k query per second. So definitely that's a lot of read operations gonna happen on this. Now let's calculate a little bit the database size or what database we are looking here. So what we will be storing in the database, as of now we will be storing the business information, right? Business information, and business will have its ID, title, description, location, contact info, and owner, email, etc. I think this will be the information we will be storing. So we have list of business with their lat long, with their location information, and maybe we might need a business type also, such that it is a gas station, it is a grocery store and all. So now I have this database. So if you see, let's make assumption here that we have 500 million business in all registered to our application. So if we see ID, title, description, so these all are more or less text. So ID 8 byte, title could be 50 words, so 200 byte maybe, description 250 words, 250 letters, so it could be 1000 byte. So in all, I think 5k seems to be a good database size, 5 KB. So the total DB size will be 500 million into 5 KB, right? Will be equal to 2.5 into 10 raised to power 9 KB. So 10 raised to power 3 KB is 1 MB, 6 is 1 GB, 9 is 1 TB. So it will be 2.5 terabyte data. So this is definitely huge data. So we will prefer shard it. We will be sharding. One more thing, we have a heavy read operation. This is a heavy read and like not too much write comparatively to read. So we definitely need multiple read replica. One server will not be able to support that entire load, especially in the peak hours. So we need the read replicas. So if we have to store the business pictures, so we might need to store the pictures, and those pictures will be stored in a blob storage, and we will use S3 blob storage for pictures, and the URL will be saved in this table. So we have the S3 blob storage for pictures, we have database, we will have owner also in this. So we have a users, owner, and all those, and there will be a relation between this business is owned by this particular owner. So I will suggest to go with relational DB here, and let's use the SQL DB for the business information. So I think we understand now. We know this is a heavy read operation. We know it's a relational database. We have a high level idea of the database size, and we're going to use S3 blob storage to store the pictures. I'm not talking too much about the pictures size, because a business may have 3, 4, or maybe 5 pictures, 10 pictures, even not a big deal. So I'm not like too much spending time on that. If you want, you can consider like, okay, 10 picture per business, and there are like 500 million businesses, and one picture size, you can put an average picture size, maybe certain MB, KB, whatever, like and you can do a simple math. So okay, so now we have successfully done the capacity math. So it's time to get into high level design. So here we have user. There is one more portfolio here for the user, and that is the business owner, right? So we have actual user using our application to find the nearby location, and we have the business owner. So there are two portfolio here. So what these will do, the business owner will create, update, delete the business information. So it will there will be a business service which will so user will connect to business service, and business service will we have a SQL database we talked about. So here is our SQL DB. I call it SQL also. Some people call SQL, some call SQL. So, and we have the blob storage here for the images. And here in the SQL DB, we have table for business. We talked about that. ID, title, description, lat long, contact info, and business type, and URL, and owner ID maybe. Then we will have another table which will be majorly having the user information, ID, and name, address, or maybe contact info, email and password, email, contact info, and address. So this will be user table, business table in the SQL database, and we have images in the blob storage. So when the business owner will create a business, it will make entry here, and it will store images here. So now the information is there. So now this user will say like give me the nearby business. So this is like, let's say, location base service base business service. So this will say like, hey, give me the nearby business within 5 mile radius, and the service will go into the database and will see like, okay, this is the lat long, can you give me the business which are like plus minus 5 mile range for the given lat long, and then we'll send back the response to user. So that's how this will work. So if you see from functional point of view, list all the business in given radius and lat long, our design is providing the list of businesses. Second is business owner should be able to add, update and remove the business. So our business service is providing the support to do all the CRUD operations on the business. So we have kind of covered our both the functional requirements as part of this business. Now the interesting part begin here, that is non-functional requirements. And non-functional requirements says the first thing is the latency, the low latency. Now if I will ask or write a SQL query to fetch all the businesses where their latitude is within plus minus 5 of the given latitude, and in that filtered result the long is plus minus 5 of the given long. So that will definitely not be low latency. Even though if I will do indexing, I can do indexing on both latitude and longitude separately, but when I will have tried to fetch the intersect of both of these fields, the performance will start hitting and it will not be low latency. So I need a better way to handle this case. So what should I do? Let's talk about that. So basically to handle this, there are different approaches out there available, and the most popular approach comes out there is the geo hashing. The first is geo hashing. So in the geo hashing, if you have seen my video where I have created a system design of Uber app, there I explain a little bit about how the geo sharding happening, how the entire space is broken down into polygon shapes, and a cluster of server is managing those shapes. So that is the concept we do here. So basically what we do in the geo hashing, we take the entire map of earth, and what system do, system create small segments of that map, and it start giving unique ID for each segment. And now when users search for a particular given location, system look for the segment in which that user location exists and fetch all the data from that particular segment. That's how a high level idea it works. Don't worry, we will talk a lot about this because that is the key part in this entire design. So that is what geo hashing. There is another way, another concept to handle this situation is QuadTree. In QuadTree, what it does, it actually generate it's a data structure actually, which is a tree type data structure where, like, you know, consider it like we have the entire earth map at the top, then we split it into 4 quadrants, and each quadrant is further recursively keep breaking down into 4 quadrant until we get the desired size of the node, and we call that a leaf node where we have all the businesses. And the third is, which is we call Google S2, and Google S2 is basically used by Google Map, and Tinder also use the Google S2 library. Tinder like to find out the friend for like the user, the nearby located friend. The Tinder use the Google S2 library. Let's try to understand these three in detail. That will help us in what direction we want to go from here in this design. So let's talk about all these three different algorithms. So let's begin with GeoHash. So as you can see, this is kind of a two-dimensional map for Earth. So what GeoHash does, GeoHash start splitting this entire two-dimensional space into equal size of segments. So here you can see there are 4 segments we have, and it gives the ID for each segment. So first is like 01 and 11, 00, 10, and then it further split each segment into 4 equal size of segments and append the IDs to the previous ID like 0101, 0111, 0100, 0110. And what it does, it is actually keep breaking down the entire space into small segments until it reach up to a desired size of grid. So here you see the first segment here. I further broke it down into 4 small segments and appended 2 more digits into ID of each segments. So every time system split the segment into 4 small segments, append 2 binary digits into the ID of those segments. That's how we will traverse down from the root to the individual segments. So once we have the desired size of grid, we have a long binary number as an ID of each segment. So what this GeoHash algorithm does, it do base 32 hashing to convert these long binary into a fixed number of size of hash length. So what it does, when you see that if your binary digit number is up to 5 times 1, the length of geo base 32 hash will be only 1. And as you keep increasing the binary digit number, the geo hash length will also be increasing. Let me show you using a binary number to base 32 hash conversion tool. So if you will see here, from binary 1111, the base 32 hashing number length is 1, that is V. But as soon as I append one more letter here, the base 32 length are now to be 2 digits, 1U. And similarly, like if I will keep appending letter here, it will turn out to be bigger number, not very sorry. As you can see, so this is now length 6 base 32 number VUEQQ, as length of base 32 hashing is 6 here. So now you see that when we are increasing the binary number length, corresponding base 32 geo hash length is also increasing. So to give you an idea, the geo hash length 4 size becomes approx 39 kilometer width and 20 kilometer height cell, the grid size. And when you keep splitting it further and your geo hash length becomes 6, the grid size reduced to 1.2 kilometer width and 600 meter height. And if you keep a further splitting the the grid cells into 4 equal size of segments and your geo hash length becomes 8, the grid cell size becomes 38 meter width and 19 meter height. So now you can imagine that if you have to find a business within 20 kilometer of range, you most probably will be storing geohash of 4 length. You will be breaking down the cells up to 39 kilometer width and 20 kilometer height, so that whenever a user in that particular segment asking to give the business within 20 kilometer, you can just pick that particular geohash ID of length 4 and show the businesses in that. But if your requirement is, you might want to give option to user, where user has option that okay, show me the business of 20 kilometer, like he has option to choose different radius. So you might have to store data for different geohash length also. So if user is looking for businesses in 20 kilometer, you have a data set where the geohash length is 4 and corresponding business IDs in that segment of 39 kilometer width and 20 kilometer heights are stored in the database. And if the user is interested to see the business within 500 meter range, then you will go into your database and see all the businesses exist with the geohash length 6 for the particular user. So that's how you're gonna do. So let's take a look how we will storing it in the database. So in the database, you most probably will be having two columns, GeoHash, where you will have the ID, and the ID, it will store the GeoHash ID, which is like base 32 hashing. And depending upon your requirement, in our system design case, we want user to have an option to choose radius. And we have not especially talked about, but I'm pretty sure, or I'm assuming, that user most probably will be looking from 500-meter up to 20-kilometer range. So we will be storing GeoHash length 4, 5 and 6. All these three GeoHash length we will be storing in the database. So we will have all the segments when we split the entire earth having GeoHash length 4. Then we further split it down into small segments. When our ID becomes GeoHash length 6, we store all that information corresponding to those small cells and their businesses. And then we further split down and then we store the information. So now we have the segment ID and the business in that segment. So now when user will say like, hey, give me the business, we will see which segment user lie in, what is the radius he is looking for. Accordingly, we will go in database and figure out all the businesses in that segment and show them to user. Now there is the problem. What's the problem? The problem here is because we took the entire map in two-dimensional and start splitting into small segments. So you know that approx 29% on the earth is land, rest all is water, ocean, sea. So lot of our grids will be over the sea and there will be no business. So it's like ton of data there we will storing in our database, which is not useful from our requirement point of view. And at the same time, there will be the places where we have very dense populated area. For example, if you will have a grid in New York, there may be thousands of business within a grid cell. And similarly, if it is somewhere in outer location of a state, it may be no business or very few business. So basically what is happening, data is unevenly distributed. To solve this problem, rather having equal size break the segments, what we can do, we can put a check there that split or break a segment only if there the number of business is more than a particular number. In this case, in this example on the slide, I note down like I took the 100. So if my segment has more than 100 business, I will go and further split it into 4 more segments. And once I reach the limit, or like I have less than 100, I will just use it as a my final segment. So in this way, the data will be evenly distributed. The another problem which most probably you will already be thinking about, and that will be the borderline location issue. So if a user is located at the boundary line of the grid cell, so there may be the case that when user is asking that give me the restaurant or nearby restaurant, the restaurant within the user cell is comparatively far than the restaurant in the neighbor cell. To solve this problem, what we can do, we can get the information of businesses from the user cell and all its neighbor cells, and that will be constant time calculation. We can do that. So every time when a user will ask, give me my nearby like restaurant or gas station, we will just go and we will fetch the business IDs from its own cell and from the neighbor cells and find the distance to each of them to get the appropriate list. So how it will look like now? This will look like something this. So as you can see, the size of grid cell where we have less dense populated area is kind of much bigger comparatively to the size of the cell which is like located in a dense area. So now the cell, like the data is evenly distributed. So if you are storing the information of each cell ID and corresponding number of business, so there will be like evenly distributed data in your database. So now, so far we talked about the geohashing. Now we know what is geohashing, how to split the space into the segments, and
how to generate the base 32 hash ID for each segment, how to store database corresponding to each segment and business information. Now the second thing comes here is the QuadTree. So what is QuadTree? QuadTree is a data structure that is generated recursively subdividing space into 4 quadrants until it meet criteria like number of business are less than 100. I'm just taking an example of 100. So you can define a criteria here, and once the criteria is met, we stop further breaking down that particular quadrant. So every time we have we pick the, so the difference here is that we are breaking down based upon the defined conditions. So let me show you how it will look like. So this is like the earth map, 2-dimensional map. I started breaking it down into 4 quadrants. So see, rather thinking about the space, how much, what is the size of space, we are saying here that we have the total 500 million business. We split into 4 quadrant. Now we have 100 million business in one quadrant, 50 million business in another quadrant, 200 million and 150 million. And further we break it down and we keep breaking down until our condition met. And in this case, our condition is that number of business in that quadrant should be less than 100. So all the leaf nodes in this tree structure, if you will see, has less than 100 businesses. So if you see how to store this data, for the non-leaf nodes, we will be having the ID, which is like 8 byte, and then grid top left and bottom right coordinates. So you know, like the map, we are splitting it into quadrants. So each quadrant, top left and bottom right coordinate, which will be kind of like 32 bytes in the side, 8 byte into 4, which is 32 byte, and then pointer to its 4 child nodes, which is 32. So, and now at the leaf node level, there we will have the list of business IDs, and it could be maximum up to 100 because that's our condition. If it will be more than 100, we will further split it down. So it could have maximum 800 byte information for business IDs and then 32 bytes for the coordinate of the grids and ID 8 bytes. So you can see how the entire space is broken down. So how to traverse in this? Like if we have to figure out or we have to find out the number of businesses in a particular quadrant, we will start from the top, traverse through the tree and reach onto that leaf and figure out what is the number of businesses in that. So here the problem is, think a scenario that a particular leaf node is like all the businesses from it getting deleted. So what you do in that case? Or sometime like if the business is like going more than 100 in a leaf node, a lot of new business got generated in a particular area and the number of total businesses are going up now more than 100. So these all kind of things where we have to rebalance the tree, it's not so simple. And one simple way to solve them could be that rebuild the entire tree. And because our business requirement is that we are okay if we show any new business added into the system or updates up to delay for a day, then it's not a big challenge to create this new QuadTree because I think it is few minutes job. Only thing is that for the time when we will be creating new QuadTree, we can't have our business down. Our service should keep running. So we most probably will be having multiple replicas of the QuadTree stored in different server so that we can create a new QuadTree. And in the meantime, the service is still working fine with the older data or the older QuadTree. Once the new QuadTree is in place, that get in, updated across the servers. So this was actually about the QuadTree. As I said, in our design, we will use the GeoHash, but it is very important to know this a different algorithm what we use, a different data structure what many applications use today in proximity services. So here the number of leaf nodes are equal to 3 into number of internal nodes plus 1. So as I said, the problem is in case of leaf node has no more business left or go beyond 100, we need rebalancing, and that's a challenge. And we have to create the entire QuadTree again, which may take few minutes. And we have to maintain copy, and in the meantime system will show the still data. We already talked about it. One important thing here is that this QuadTree, because we will keep traversing it, we might want to keep it in the cache, and because we have to maintain multiple replica of this, so Redis cluster is a better option, or the best option, I think. So we can use in our system if we want to use the QuadTree, so that, like, we will have multiple replicas, easy to scale up, and highly available. So we will achieve all the things what we need for our service. So that was majorly about the QuadTree. So now we talked about the geohashing in detail. In geohashing, we were splitting the entire two-dimensional space into segments. In QuadTree, we have a data structure where we were maintaining a tree structure. Now the next thing comes is like S2 Google geometry. This is little complex. The core concept, as I said, is same. We are splitting the information into small segments, splitting the space, but rather using the two-dimensional space here in the Google geometry, they have the sphere shaped earth they used, and they split it into small segments. And to do that, what they did, so this seems little complex, guys, but if you will stick with me, I'm pretty sure it is not so complex as it looked like from the diagram. So here you see this sphere in the center is the earth, and then draw a cube around this earth. Imagine there is a cube around this earth. This is three-dimensional. So this is a cube which has all faces across all sides, and the sphere is like within that cube. Now, if you will try to project these points, for example, the point P1 here on the earth is projected onto this cube. This will be a point on the cube which is three-dimensional point x, y, z. And for this entire direction, entire side of the cube, x1 coordinate will be fixed. That will be the x coordinate. Similarly, for the top one, the y coordinate will be fixed, and the z will be fixed for the side ones. So, what is happening in this case, if you will see, that point P1 is projected from the center on this cube, and we started calling it XYZ. Similarly, further points on this entire sphere all are projected onto that cube. So now you see that this cube has kind of like entire earth point projected onto this. But the problem here is, if we start drawing cells on this cube now, if you will see, space 1 of the sphere is covering area on cube 1, and here this is not cube 1, it should be area 1 on cube, and this is area 2 on cube. And if you will try to break it into small blocks, the area 1 on cube will have 2 blocks, and at the same time area 2 on the cube will have the 1 block, as I am showing it with the red color lines. So basically, space 1 and space 2 on the sphere, which is earth, is same size of a space, but when it is getting projected onto the cube, the size on the cube covered by the projection is different. So you can see that the data, if you will start breaking down on the cube each area into different cells, it will be unevenly distributed data, because some point the same size on the sphere is turning out to be 2 cells. At the same time, some space on the earth is coming to be as a 1 cell of the same size on the cube. So if you will see here, what we can do, we have to apply transformation on that cube. So we have the sphere, keep in mind, we have the sphere, and we cover the sphere in a cube, and then we projected from the center entire sphere on the cube. Now we have the data points or the location points on the cube corresponding to each point on the sphere, and the size covered by the same space on a sphere is different on the cube because of the projection angle. So what we do, we have to apply transformation on this cube to make evenly distributed data. So what we do for the transformation here, as you can see, corresponding to the face, this face of the cube where we have point face y and z, I have another line drawn, and that is showing the further transformation of the points onto face st. And this transformation could be different, or it will be multiple layer of transformation. And there are different options. You can do linear transformation. In case of linear transformation, the maximum space covered by a cell and minimum space covered by a cell, the ratio of them is 5:2. So this is like unevenly distributed data with the linear. But at the same time, if you use the tangent, this ratio will be 1.41, max size and min size covered by a cell. And this is like more uniform data. And then another transformation algorithm, that is quadratic. If we use the quadratic transformation, the ratio becomes 2.08, and but it is much faster than the tangent one. So basically what they do is, they just be with me and think again about it. We have the sphere shape earth, we cover it in the cube, we project all the sphere points onto the cube. Now, to make sure the data is evenly distributed on the cube, we perform number of transformation, and those transformation is basically to make sure the data is evenly distributed, there is a uniform data distribution, and also to achieve the desired size of cell what we need. So at every layer of transformation, our size of grid is also reducing to reach up to the desired size, and at the same time we have more data, uniform data distribution. So if you will see the cube face, how it will look like, this will look like this, that entire cube has a small cells broken out, and each cell we broke it in S2 library. We broke it each cell and give a 64-bit integer ID. So using 64-bit integer ID for each cell, we can break the entire space up to a square centimeter. So we can just each square centimeter space of earth, we can create a single cell and we can give a ID. That 64-bit integer ID will be supporting it. So we have pretty highly scalable uh, system in this, and we use the Hilbert space curve to enumerate, to traverse across these cells. What is Hilbert? Hilbert, as you can see on this screen, it is U-shaped type thing. It's not like linearly you are going through each uh, cell. So basically what it does, it actually makes sure that all the neighbors cells should come next to each other in a one-dimensional data. So it begins from a cell, it go in the U shape, cover all four next to each other cells, take their IDs, put them onto a linear 1D data, and keep looking through, keep moving in U shape, zigzag shape until it reach up to the end. So what we will have at the end? At the end we will have a one-dimensional data which is very fast to search, and we will have all the neighbor cells together on the one-dimensional data. So when we will have a request that show me friend near me, near my location, so it will just look in my neighbor cells within given radius and quickly find out on a one-dimensional data that this is the section. We have to figure out, okay, these all 5 friends you have, you can just reach out to them. So this was the Google S2 library, guys. So now we talked about geohashing, we talked about the QuadTree, we talked about the Google S2 library. We understand now the backend logic, how those works. We understand how the data they stores. So as I said, in our design, we will use the geohashing, and if we will be designing Tinder, very specific application, and we have requirement for like Tinder or Google Map, we know that Google S2 library they use in the Google Map, so we can just use that also. But we are not very specific talking about, we are trying to use a generic algorithm which is most popular out of them. So I'm picking just GeoHash. So let's go back to our design.
So as we already talked, we gonna use the geohashing here. So let's start drawing it again now. So we have user, and user will reach out to location service. Location service will look in the Redis cluster, and what it will be? It will be GeoHash ID and the business ID. So now this will be looking here, it will go here. Okay, for this location, for the user location, look in the data what all different businesses available, and then there will be initer caching. So this is business info, and this is also in the Redis. So the service will look through the business info in the Redis, from the Redis, that okay, what is the business details for these IDs, and then there will be a SQL DB which is having the permanent storage as we talked up there, and a S3 block for the images, yeah, and update the caching also. So now you can see we have location service. So user is saying like give me nearby restaurant, it will go in the Redis cluster and look for the user GeoHash and find out all the business in user GeoHash and all its neighbor GeoHash hashes, and like get all the business ID, look in the cache and get all the businesses, and find what all different businesses are in the radius and return back to the user. So now because we have the Redis in place, it's a fast application. We are not looking through million of rows, we are just focusing on those particular geohashes which are like neighbor of the user. So a small set of data, so this will be low latency. In location service should be horizontally scalable, and to do that we have to take out the session from this, and we will have a load balancer here. In all videos we talked about this, we know pretty much about load balancer now. Basically redirect the request to uniformly distribute the load. Then we will have the gateway here, and this gateway will be having session service here, so that the session DB and session service will be out of our services location, and these, so these will be stateless. So we have the session service here, this will go to the gateway, gateway will send the request to location service is stateless, horizontally scalable, and load balancer will evenly distribute the load across different services. We have caching in place, so the request will be super fast. Now the business owner, he will send the request to load balancer, and the business service will also be stateless, and this will go to business service. Any update, edit, delete information will come here. It will go and update the database, and information images will get uploaded onto S3, and it will also update the caching information here, so that the information is available, or caching is always having the information needed for it. So let's quickly go over the functional requirement again, guys. Here, so we have latency. Yes, our system is low latency and highly available system. Our services are like horizontally scalable. Our database has the read and write replicas. So here in the SQL DB we will have, we talked about that, we will have read replicas. It's heavy read operation, and sharding will also be in place. And so we have highly available system, a scalable system. Our system is scalable, and the consistency is like when any change happening business service, it will go here, update here, and it will get updated in the cache also. So anytime service will come, it will like have always the updated information. So yes, it is eventually consistent. And we talked about our geohashing algorithm also. Like if we are using QuadTree, we have to build new tree. We know, we talked about that, but in our case, we are using geohashing. So it's not so tricky to update the things. So this is eventually consistent for sure. So I think we have good design. We did not talk about the size of this GeoHash ID and business ID. So because this will be very small, because you see like we have 500 million business, and if we are storing, let's say 3 precision of GeoHash ID, length 4, length 6, length 8, then it will be 8 into 500 million into 8 bytes. So it will be very small dB. If you guys want, you can just quickly do a simple math. And if we want to store GeoHash ID for 3 precision, like for length 4, length 6, length 8, then we can multiply by 3. So it's literally like 16 byte into 500 million into 3. That will be the size of this database. And if you want to use QuadTree in your design, just give a shot. I will suggest you to do that, please. That will give you an understanding of QuadTree size also, how much it is. Like it is very small. It come out very small data. I think maybe 4 or 5 GB maybe. It's very small. So just give a shot, try it out and see how that works. So thank you so much guys for joining the session, and I hope you learn something from this. And please try to create yourself. Just listening this, doing it will not give you that feeling unless you just open a notepad. Just open a notepad and pen, start drawing something, start noting down, do capacity math, do practice. That will, like, give you better understanding about the system design, and it will give you a list of things which becomes either unknown and you want to read about them. For example, Google S2 library, I explained this. There is very few information out there about this. That's a lot of document books I read to understand this. And the different transformation, that is kind of like transformation we use in machine learning, and they used it here. I did not get too much detail into that because that is more for the machine learning point of view things. There people know how the linear transformation works and all. But if you will try to do something, you will get a chance that okay, these are 5 items where I should learn a little more to understand it better. So try to do it, and please don't forget to subscribe my channel. And thank you so much guys. Thanks again.